All right, welcome everybody to the next class. How many of you have gotten into the textbook, into the guidebooks? All of you who haven't, raise your hand if you haven't gotten in yet. Why not? Okay, you might already be late on the homework assignment. I don't know. Does anyone know if anything's been assigned yet?
Nothing yet.
Nothing yet. Okay.
I emailed.
Yeah, look.
Yeah, I emailed them asking him like, is there a general guide? I never got an email back because there's just chapters and then the challenges in the chapter. So we have like 50 of them. And there's no time frame for us to read.
Okay, well, the reading, you can always go and get ahead and read. Right now, we're going through chapter 1, the main section. Now, the assignments will come from him and they will be inside books and they will each have a deadline. And I'm really surprised there aren't any yet. And that surprised me, so I'm gonna get on his case about that. Now, in terms of the actual book, you will see, let's get to it. I thought I had it up. Okay, what we've been going through in class is all the chapter 1, 1.1, 1.2, 1.3, 1.4. You will recognize some of the visuals even, but definitely the topics. And I would suggest you stay ahead. So I'm probably at like 1.3, 1.4 right now in the textbook. That's the content that I've been talking to you about. Try to stay ahead. Try to get to chapter 2 before I start chapter 2. And I'm going to speed up. So I've been going slowly recently, but I'm going to start speeding up so that we can reach all the chapters before the end of the semester, obviously. Any more questions about that?
In terms of homework, what can we expect?
So either it will be one of those challenges or one of those other things. These are all assignments within Zybooks. They're all things you do in that whole ecosystem. And I don't actually know how many of them there are. You can see them all in the book, and they may not all be assigned.
I think the reason why he hasn't listed anything is because the next item has to do it.
Oh, really? Okay, that may be the reason. So we're skipping the boring things that are just, you read this, and then you say you read it, and there's some stupid question. We're done doing those. But we're doing all the ones that involve actual challenges and coding and things like that. So you can use your time, homework time, to read, get ahead, and decide your data set for the semester-long projects. Who has an idea so far of what they might do? All right. Keep thinking. Do you have any questions about that? About what might constitute a good?
If we have a data set and we wanted to add our own data that we collect, would there be an easy way to do that?
Yes.
Okay.
So if you have a data set that's going to have certain fields, like let's say heart rate, where you have to collect your own heart rate too if you want to add to it. You don't have to add your own data to it, but that is a good thing to do. I like that. So you got to have a Fitbit or an Apple Watch or a Whoop. There's like 30 of these devices now that you could have. Or you can even sit there looking at the clock and counting with your finger if you really wanted. Does that answer the question?
Oh, I just meant like in these different like formats that we would download these data files in. They would all be modifiable manually.
Oh, everything is modifiable by you if you want. Think about this. Whatever you get from the internet, it's got to be in a format you can read. And if you can read, you can write. So if it's a CSV file, that stands for comma separated values. Ironically, the best CSVs are not separated by commas. Why is it a bad idea to separate your data with commas? Potentially.
Some values like thousands, millions.
Yeah. Exactly. What if you have some data set that has, you know, name, address, the value of a home loan, let's say, of loan, and then the status. And there's commas between each. Let's say some guy's name is John Smith. Then there's a comma, and this is some string. And then there's some address. That's a string. So it's one thing, okay, it's not going to get split up. But then we get some number. And let's say somehow in the file, even though it was a floating point or an integer or whatever, it got listed, it got printed with the commas in it. Like let's say it's $500,000 and the status is current. Well, if you just use some naive CSV parser, it's going to think that the value of the loan is $500 and the status is 000. That's not good. So CSVs are best done with a different delimiter, but you can't control them when you're downloading it. Let's say you just download it from the web. It's probably going to be commas, but you can check. Whenever I make a CSV, I delimit them with tabs. And I make sure, of course, there's no tabs anywhere in the actual data. And a tab, if you're printing from in a program, you would print a tab. If you just wanted to do a tab with \T, that's how you print a tab. And a tab looks just like 4 spaces or so, 5 spaces, depending on the situation. But this is how you actually print it. And what you'll learn is that what the computer thinks and what you see are 2 separate things. How things render is different from what's actually behind the scenes. For instance, there's something called Unicode. You guys ever heard of Unicode? Unicode includes not just our alphabet, but almost every alphabet that exists on the planet. And there's even different kinds of Unicode. And if you have a Unicode letter that's one of the alphabet letters in our alphabet, and it prints or a word, you actually can't tell just by looking at it. Is it Unicode behind the scenes? Is it ASCII, which is normal text behind the scenes? What is it? You don't know. That's why if you have some word 1 and word 2, and they're separated by some space, and it's just printed out, you don't actually know if that's spaces or if it's a single tab character. But the computer knows, and the computer doesn't get confused. And if you decide to have a CSV that instead of commas, it's using tabs, the computer will never get confused. But it does mean you got to make sure your strings don't have tabs in here anywhere, which is typically easy. Okay, now let's say you found a CSV out there on the web, you downloaded it, you even wrote Python code to read it. And we will do this together maybe next time. Then you have total power, you have total control. You can process these values, you can convert them to something else, you can convert the dollars to the British pound if you want. You can convert addresses to latitude and longitude if you want, and then you can print it all back out again. let's say that you have a CSV, which is in a slightly different format than the data you want to collect at home. Just start collecting data. Collect a bunch of data at home, then you'll write a process to read in your data, read in the CSV, then print it all out together in the same format after doing whatever conversion function you need on the back end. And these are all good thoughts and questions, and I'm going to take notes on things to add to the next lecture. Once these are values in your program, you can iterate through them one at a time, and then you print out each line in whatever way you want, whatever delimiter you want. In Python, there is a CSV package, and you can make a CSV reader or a writer. They both work pretty similarly, and there is a way to tell it what you want the delimiter to be. I think it's called delim. You just set it equal to something, and as I said, I always set it equal to \T. Did I answer that question? All right. Are there any of you who actually want to work in data science after you graduate? Raise your hand. I do already, so. Okay. These are some of the common job descriptions. And they could be all over the board. They're not very precisely defined by anyone. And some of them are just made up not too long ago. Does anyone have any contacts? Anyone you know who does one of these things? Family member. Tell me about that person. Ooh, brain scans. That's very interesting stuff. So is she using visual neural networks at all? Nice. Okay, so we'll go down the top. Data scientists. Yeah, we all kind of know what data science is, kind of, right? The guy I showed you earlier on in the slides, Shama Palihapitiya, was one of the early guys at Facebook. They were hiring someone who was kind of a big name, and they said, we want you to work with data, and we're going to call you a data analyst. He says, I don't like that. How about data scientist? Sure. And he was supposedly the first data scientist of the modern era. It just means writing code to deal with data, maybe all the back end stuff that goes with it, and anything your boss needs regarding data or analyzing it or even building models from it. So it's not very precisely defined. A data engineer is typically someone who will not do the machine learning part. A data engineer is not going to be doing something creative. That's one of the distinctions that I find. To be an engineer, you have to make sure all of the I's are dotted and the T's are crossed. You have to be really good at details. You don't have to be good at creativity at all, really. But you cannot drop the ball. We need you to be precise about everything you make. It has to be robust. You can't have memory errors. You got to write things in a way that are scalable, inexpensive. That's what I would expect from a data engineer. And the word engineer means it's engineering, meaning if we give you something you have to do, maybe it's 2 weeks, maybe it's 4 weeks, but it's a known amount of time. If something is engineering, it's well understood. When I think about engineering versus not engineering, I'll think the other side is science. I'm not talking about the scientific method, I'm talking about more about research. So maybe science is over here, and these are all the things that we're exploring, we don't understand quite yet. And then engineering are all the things we not only understand them well, we've got textbooks for them, courses for them, and when you have a given project, you know how long it's going to take. Over here, we put construction. Think about building a new building, like the Boyer building next door. When that thing was scoped out, they had pretty much an idea of how long it would take, how much it would cost, how many people would be needed, what would be the materials. Now, no project goes perfectly, but that's engineering. Science is more like, instead of building a building out of materials we've understood, maybe we'll grow a building out of carbon nanotubes. Something no one's ever done before. That would be over here. Now, data science in general can lead to different kinds of jobs, and some of them are the creative ones. Like we have some data that no one's ever been able to model accurately before. What model do we use? Have you guys have played with ChatGPT, I assume. That is science. That's the newest thing. Working with transformers, making them bigger. Everyone's studying this. Like, how much bigger do we have to make it to get 1% more accuracy? And it's like they got to spend like $10 million more for every 1% accuracy. It's not easy to scale. Okay, a data analyst does something different from an engineer. A data engineer is going to engineer where the data is, the cleaning functions, maybe ETL, extract, transfer, load, and everything that's needed to support other business functions, maybe the machine learning engineers, for instance. But a data analyst just consumes the data. They don't manage the back end. They just take the data and they try to draw conclusions. Maybe they're creating visual representation. And they're telling their boss, you know what? We shouldn't sell t-shirts in our stores in the winter because no one buys them. Things like that. Anyone know what BI stands for? A BI analyst.
Is that business intelligence?
Almost, business intelligence. And Power BI is a Microsoft product that allows you to take some data set and put it in their Power BI website app, basically, and visualize it in different ways. They kind of do the same thing that the data analyst does. A BI analyst is just doing business data, focusing on that. And they may have a better idea of things that people care about in the business world, like tying profitability back to product lines, or certain employees, or certain offices. A machine learning engineer. Now, even though this one has the word engineer in it, most machine learning engineers, I find, are doing something more like science. They're given some data set or access to data, and they're asked to model it. Maybe that means use a random forest or XGBoost or neural networks, or come up with something else. But they're usually asked to construct the whole pipeline, get the data, do the training, and get a model that's usually represented with a file. You're doing PyTorch as the PTH file. There's a couple different TensorFlow formats. There's lots of different files that we use to store the guts of the model. But then how do you use it? What you typically do these days is you put it in a Docker container. Who here has heard of Docker? All right, you're all gonna have to do this someday if you work at all in this field. So there's more than one kind of container. Docker is merely the most popular. When you have a software system, package, whatever that you've written, you're not writing every line of code yourself. you're importing modules. And when you start working on this, on your homework even, you're going to be importing things. And in Python, that's just import this, then import X, import Y, whatever. You import these modules, then you can use them. So you don't have to rewrite a whole lot of complicated code that other people use. But what happens if one of those things you import gets updated in some little way that breaks your thing? You don't want that to happen. Or there could be something underlying in the actual operating system. Maybe you're using Linux Ubuntu 2004, but some little update occurs for security or who knows what, and that breaks something you're doing. People don't like this either. So how do you make sure that doesn't happen? And the way you do that is inside of the server that's running Linux or Windows or Mac or whatever it is, you run a container program. And again, the most popular one is called Docker. And what it does is it gives you the ability to run what is almost a virtual machine. It's not quite, but it's most of the way there. So you'll have you can think of it as a box, this container. And inside here, you decide what operating system you want it to be. And I usually use Ubuntu. The most popular one right now is 2004, but I use Ubuntu. And in here, I make sure that I have the right version of Python, and I make sure that I do pip install of all the right modules. And then I have my system, and it's just right. I don't change it. It's stuck in a container. It's a static thing. And then I can save that whole thing as a file. It's like saving the image of your whole machine in a sense as a file. And then I can run that anywhere Docker runs. Amazon even has things like something called Fargate, which allows you to scale up semi-infinitely. You can say, you know what, here is my image, my container file. I'm going to register it. And you can register it with a container registry. And the Amazon one is called Elastic Container Registry. So you basically, it's just a way to save it. So you just save it in there. Then you can tell Fargate, I'm going to spin up one, but if I get people using it, spin up more to match the demand. And Fargate will spin up copies of this computer in a sense. Maybe one, maybe two, maybe three. And you don't have to worry about the details. It takes that container and spins up copies of it. And every one of them will be running the machine learning model that you trained. And if we're taking the example of your cousin back, let's say you have a model that can find brain anomalies. Well, if it's the middle of the night and no one's using it, maybe it spins down to 1. But then as soon as people come in the office in the morning or in the hospital and they start using them, it spins up 2, 3, 4, or 5 so that it can handle the workload. This is what a machine learning engineer would know how to do. Now, they also oftentimes have help from other engineers who don't know anything about machine learning, but they can handle with all the AWS stuff or the Google Compute Platform stuff or whatever it may be. And you might call them DevOps. That's another job title that dovetails with this. An AI developer could do everything a machine learning engineer could do, but they also are knowledgeable about older AI systems. So forgive me if this is a repeat, but all of AI and machine learning can be described as type 1 and type 2. Okay, given that definition, which one is neural networks?
Type 2.
No.
No.
Type 1, here's why. If you have a neural network, you have some input, right? You got your input. Maybe it's, let's say, it's an image. Maybe it's a cat, maybe it's a dog, and your network is trained to differentiate cats from dogs. That image is really just a bunch of pixels, right? Maybe it's 1,000 pixels or 1,000,000 pixels, and those pixels come into the network. The way they come in typically is you have one neuron for each pixel. Or alternatively, maybe you have 3 neurons for each pixel. Why would you ever have 3 neurons for a pixel in an image?
There's 3 RGB values.
Exactly, RGB. So you have, let's say, 3 neurons for each pixel. And all you do is you take the value of that pixel and you're going to have each neuron process it through the network. And every time a neuron processes information, it does something very simple. Let's say you have, I'm going to do a close-up on some part of a network. We have one neuron, we got a number coming in. Let's say it's the number 52. Now this neuron is connected to typically every neuron or a lot of neurons in the next layer. There's convolutions and other complications. We won't get into that right now. Every one of these connections, these outgoing connections, has a weight. So you've got weight 1, weight 2, weight 3, etc. Whatever value comes from here, and since it's the first layer, it's just straight up the number. So 52 comes out this thing and it gets multiplied by W1. Comes to some other neuron. That neuron right here is the first layer that's actually doing processing. It's going to take 52 times that, and it's going to add a bias. Every neuron has its own little bias. So this one has bias 1, and bias is just a number. So let's say the number here for bias 1 is 0.003. It doesn't matter, just some bias. So this weight times this number, this bias, and then as it comes out, we do a little bit more math to it, something called an activation function. But it's just math. So basically, every neuron does a math problem. The same math problem every time, right? If you have in your network, in all your layers, let's say if you counted up all the neurons, let's say it's 1,000,000 neurons, okay? And then you have some output layer with only 2 neurons, one for cat, one for dog. That's a simple example of what a neural network is. So, pixels come in, every neuron does its little math problem. Just a little bit of multiplication, a little bit of addition, all the neurons do their part. In the end, we end up with 2 numbers. Whichever one is higher, that's what we say the class is. If the cat number is higher, we go, oh, it's a cat. Otherwise, say it's a dog. If you have a very difficult example that even a human can't quite tell what it is, the neurons will do their thing. They will do a certain number of computations. If you have a really easy example everybody knows instantly that's a cat or that's a dog. The neurons will do the same number of additions and multiplications. There's no ability for it to handle complex situations any different than it handles simple ones. Can any of you think of what would be type 2? So neural networks are type 1. What on earth is type 2?
They call it deep learning.
No. Deep learning is this. Deep learning is if you have, it's arbitrary, but people used to say if it's more than 5 layers, it's deep. Then if it's more than 20 layers, it's deep. But deep learning is the fact that you have many layers in your neural network. Oh, that would be great. Yes, we're actually probably a long way from that. But there are type 2 systems that are definitely not conscious.
I mean, in a way, aren't our computers type 2 systems?
They are.
Like when your CPU ramps up, it's because it's dealing with something more complex.
Yes, exactly. And sometimes it takes away resources from other things. Whenever you have a program that can conditionally branch, that's typically type 2. And conditionally branch especially to do more or fewer computations. Have you guys ever heard of first order logic? Have you guys ever proved a theorem in math class? There are programs that can prove theorems. Think about what that would take. When you try to prove a theorem, you often go down dead ends and have to backtrack, right? That ability to look at something, see where you are, go backtrack, and try again, that is definitely type 2. Playing chess can be done in a type 2 like situation, where if you only have one piece left, you really don't have that many options. But if you have, 10 pieces left, then you have a lot more options. And you play forward, 1 move, 2 moves. You imagine all the possible moves your opponent might make at any given point. You play the game forward, 5, 6 future moves. That's type 2. An AI developer should be cognizant of type 1 and type 2 models. But often these days, a machine learning engineer only does type 1. And type 1, it can be neural networks. Random forests are another very effective thing that I like. XGBoost is similar to that. Any questions? Okay. Whenever I'm actually doing something real, an application that needs to be used, maybe it's for a startup or a big company, it doesn't matter. Almost always, you need these 3 tasks. Every now and then you get a full stack developer, a guy who says he can do everything. And some of them exist, whatever. But I like having them be separate jobs. The front end, this would be JavaScript. This would be Vue. This would be Angular. Anything that makes a website be what it is. And the front end interface, something you can interact with. And it's not just making it look pretty or making it do the functions you want, but typically you want this person to have an idea of human-computer interaction. What it means to be a human computer, interacting with a computer. What's natural, what's instinctive. There was some effort in the early days of apps to come up with kind of a physics for apps. We all understand the real world, You drop something, gravity speeds it up, and you all have an intuitive sense of 9.8, meters per second. That's the average acceleration of something at sea level on Earth. When you swipe up on a feed or down, it keeps moving and then it slows down, right? Right? Does it slow down because of air friction? No. It slows down because the people who designed the scroll function, whatever one that they're using, and oftentimes these days they're using something called Flutter, which allows you to develop an iOS and an Android app at the same time. But that amount that it speeds up and slowly slows down, it's because that's what you expect as a human living in the real world. And they try to make these things mirror the real world so you can instinctively interact with them. A front-end developer needs to know all that stuff. Front-end languages change very quickly. Flutter is a thing now, but it wasn't 2 years ago. 2 years ago is something else. I mean, a lot of people were doing Swift for iOS, and I forget what for Android. But before that, it was something else. Before that, it was something else. All the way back to the very beginning of the internet, the front end stuff was just HTML. In fact, one thing I'm sure none of you know is that when you had the first HTML websites going up, every image had a border. Do any of you know what color that border was? The default color. Wasn't it bright blue? It was bright blue. In fact, it was just the default, have bright blue as a border for every single image on the internet. And you had to expressly use the no border tag. And that was a fancy thing at one point. Oh, they came up with this tag, the no border tag, so you don't have to have a border in your images. Does anyone have a guess of why they chose bright blue? Why did that kind of look right to, well, maybe it was Tim Berners-Lee or whoever made that decision? Anyone watch the original Star Trek series? No? Well, did you? Yeah. The view screen in the Starship Enterprise has that bright blue border. And it's about exactly the color they chose at the beginning of the internet. Later on, they came up with these tools like Cold Fusion, which would allow you to make beautiful, complex websites without having to write every single line of HTML code. It would write a lot of it for you. Then they came up with JavaScript, which has nothing to do with Java, by the way. And then JavaScript wasn't enough, so they came up with code that allows you to generate JavaScript that doesn't exist until someone actually comes to your website and it renders. And this is the Java Vue, for example, Vue.js, Vue. There are backend things that can serve your website that are also written in JavaScript. Now, JavaScript is the front-end language. Why would you ever do JavaScript for the backend? Well, supposedly at one point, some of these front-end engineers wanted to serve up their own pages, and they didn't want to use Apache. They didn't want to use the typical tools. They wanted more control, but they also did not want to learn another language. So they wrote Node for them. And now Node is very popular and it's very stable, it's very good. But front-end languages change rapidly. Back-end stuff does not, at least not in my experience. The back-end stuff, although AWS does have more and more tools, like Fargate thing I showed you a minute ago, that's relatively new. But a lot of the back-end stuff is based on tried and true principles from computer science. Like if you get one person versus a million people using your website, you're going to design it very different. If it needs to run all the time or just sometimes, you're going to design it very differently. Okay, then the machine learning, the AI part, these people, it's good for them to focus just on the model. Given this data set, does the model perform well? I don't want them worried about human-computer interaction. I don't want them worried about back-end engineering. So if everybody focuses on what their job is and they hide the complexity of that, then typical projects proceed more quickly and have better results in the end. And in effect, what you're doing is you're hiding complexity. Like these glasses, I need glasses. I like glasses. I like them to read up close. But I don't want to have to understand the high-tech materials that go into making these lenses that aren't glass, but they're also not very scratchable and they have a little bit of a bifocal. And then there's the hinge and everything. There's a lot of complexity there. I want to go to the watches store, the glasses store, and just buy glasses. I want someone else to hide all the complexity. And they do an eye scan and they tell me what I need. I don't have to understand optics. I don't have to understand it. I just get the thing that's functional to me. So if the machine learning guy or girl gets access to data and a front end that someone else has done for them and hides the complexity of it, that makes their job easier. So yes, there are people who can do all this, but I would suggest you focus on one aspect that you like the best. All right. Any questions on what the job market is like out there or will be?
The job market gonna be like that.
So right now, it's very good for young people starting out. It's bad for experienced people right now. Have you heard about all the layoffs? Tons and tons of layoffs. Well, the ones that didn't lay off were maybe people who were doing something essential, but also people who were cheap. Young people coming in right out of school are relatively cheap, and they're still getting gobbled up. One thing that I've seen more than ever in my life is people are advertising jobs that don't pay money. They pay equity. So people were advertising jobs for, if you're willing to work for equity while we seek to get funding, then, we want you on our team. I actually have 2 teams like that right now, where I've got people working for me for equity, because we don't have funding. But this is more and more prevalent. It's not just me, it's not just a few of my friends, it's the industry. But things are going to turn up soon. So in my career, the first downturn was 2001, the dot-com boom and bust. And it was bad for a while. I even went back to working at restaurants and doing online security. Online security is actually a good job because no one would come through and I'd sit there on my laptop programming, working on future stuff, Then things picked up again around 2003 or so. Then it all crashed again in 2009 because of the housing market, right? Then things picked that back up again. And one thing I've seen, I haven't been a part of any, big, huge success yet, but all the big, huge successes that you know of, they started during one of those downturns. So something big is starting right now. No one knows what it is yet, but it's starting right now or in the next year. During these down times, there's more people out there that need a job or that are ambitious and trying to do something, willing to do something. Whereas when times are really good, a lot of people get a cushy job somewhere and they stop learning. One of the guys I went to college with, he actually went to a better college than me. He went to MIT. I didn't get into MIT, I tried. But he had a full ride and he was awesome. He was one of their smartest guys. We worked together at a company and he was amazing. And I learned so much from him. He was just so far beyond me. But then I reconnected with him again years later. And he had actually stopped learning around then. He had an awesome job, he had an awesome degree, and he just kind of cruised, it seemed. He hadn't kept learning. And when times are really good, people get really comfortable. And they stop learning, they stop challenging. So when times are troublesome or bad, like now, and things might even get harder, this is also some of the most dynamic time. And some of the greatest inventions of the next 4 or 5 years, some of the greatest companies are starting right now. So you guys don't graduate 3 years from now or so? Yeah, oh, things will be great by then. It's all gonna be on the upswing by then. That's my prediction. But don't wait till then. If you are getting like 2 years away from your graduation, you know what you want to do, start making connections. Connect to people on LinkedIn. What's that? Don't drop out. No, I don't think anybody should drop out. And I worked for a while, but then went back to grad school afterwards. And grad school for me was so worth it. Now, if you're going to go to grad school to study like basket weaving, that might not be worth it. But if you're going for a hard science, it is totally worth it. For me, somewhat undergrad, but definitely grad school felt like this. Felt like I was out in the field and each professor would tell me, okay, dig over here. And I would dig there and I'd find gold. Then we'd walk over somewhere else. Okay, come dig over here. Now, if I didn't go to grad school, well, eventually I could have learned all those things by just digging every hole everywhere in that field, right? But that takes forever. Grad school typically is a place where you get to learn where to dig and how to dig. And I learned so much in grad school. I've got my master's in computer science. And I did research. So I did a thesis in complex adaptive systems, which is, what I did is I did a model of an ecology, a model of the sea urchins and the seaweed in the Gulf of Maine, and some of the other predators in the Gulf of Maine, and the human fishermen that were interacting with the ecosystem. I learned so much through all of that. So I highly suggest you go to grad school someday if you want to be some kind of, computer scientist in the future. You don't have to do it immediately. I waited 14 years in between undergraduate and graduate school. And that was the right time because I went to graduate school during a downturn, 2009. When that downturn happened, my company had layoffs, and I'm like, oh, I don't have a job. Maybe now's the time for grad school. And that's maybe what you guys will do today. But do not drop out of school. No. Because although we talk about, oh, Bill Gates dropped out of school, and Steve Jobs, he's a college dropout. What's your probability? If you look at all the numbers, okay, you got 2 or 3 people on this side, and how many homeless people were also college dropouts? The probabilities are better to win the lottery than to be a college dropout and be some great internet success. So yeah, maybe it'll happen, but also maybe winning the lottery will happen. Don't drop out of school. That's my suggestion. Okay, the steps for any project. And these are pretty much the steps you're going to do for your semester-long project. You're doing step 1 right now. You're getting the data or deciding on it. Once you have the data, gathering it could be as simple as just clicking download on one CSV file. Maybe that's what you choose. Or maybe it's you're going to have your Fitbit and then download from it every day. Or maybe you're going to ask a bunch of friends to do that, or send out a bunch of surveys. Whatever you're getting the data onto some format that you control. Then cleaning the data. Who can tell me an example of messy data that would need to be cleaned? How about you?
Just data set that's missing a lot of values.
Missing a lot of values, that's good. What else?
Same values.
Same values? Oh, we mean again, like repeats?
Yeah.
Yeah.
So that's where data is representing different things.
Yes. Or you could have some addresses and some latitude and longitudes. So normalizing it to one thing. Or it could be meters or inches.
Irrelevant sense of data.
Irrelevant, it could be irrelevant, yes.
Would outliers count? Like extreme outliers?
Oh, this is a good question. If you get rid of outliers, are you actually getting rid of a truth you need to be sensitive to?
Yeah, I mean, you keep that out. I'm saying very, very extreme. They'll just go keep those even though they data.
Oh, this is one of the hardest questions in science. When people have outliers, they look at it and think, was this an error? Did the sensor malfunction? Or is this something I have to be able to model? Think about particle accelerators. So in a particle accelerator, you have a ton of data that's generated in a nanosecond. So imagine under the city of Geneva, Switzerland, you have CERN. Who's here heard of CERN? CERN. Some people blame them for like the Mandela effect or breaking the universe. Ever heard of that stuff? It's silly. Anyway, they have this giant ring of superconducting magnets, and there's a vacuum inside a chamber, a tube, and they will put particles in there, like electrons, protons, nuclei, whatever, and they will use the magnets to attract them faster and faster down that tube and to confine them so they don't hit the sides of the tube, the vacuum tube. And they will speed them up faster and faster. Now, we can't go faster than the speed of light. And our spaceships, with current technology, will probably never get them faster than a tenth of the speed of light. But a proton, oh yeah, we can speed up a proton to something like 0.999 of the speed of light. Really, really fast. And then what we do is we have them go around the ring in one direction and have something else go around the ring in the other direction. And then when they're both going almost the speed of light, we pound them into each other. And you'll have that moment when they pound into each other, and you will have a shower of particles that go off basically at right angles or this angle, all these different angles. When I was a physics student, I worked on a potential design for one of the components that went into CERN. My idea wasn't used, but my professor's work was somehow involved in there. So if you look at this turn this around this way. So now we're looking at what's called a bubble chamber. There's this chamber that when particles go through it that have either an electric or magnetic field, they create a trail of bubbles. And then we can see where they went. So starting at the beginning or in the middle, let's say there's one particle that goes off in a straight line. Another one goes off, curves like this. Another one goes off and curves like this. There is a magnetic field going perpendicular. So depending on which way it curves, it'll be oriented one way or the other, or it could be an electric field actually. So maybe positive goes one way and negatively charged goes the other way. And let's say we have all these things and we have all these interesting paths that these particles take as they slow down, and some of them you can't see. And the ones you can't see, you know they're there because you add up the mass, the momentum, the energy of everything that went into it, and you add up the things that you can see that came out of it, and then you can say, okay, well, this many neutrinos left, maybe this much of some other thing that we can't see. Because of mass and energy being conserved, those things must have been generated but are not visible in the bubble chamber. Okay, now let's say you do this and you look at these particles and you calculate their energies. And let's say you have, some charge and you have, a bunch of particles have this much energy, a few particles here. And then every now and then you get this one little outlier over here. And that one little outlier, what is that? That must be a mistake. Maybe I should just throw it away. Or maybe this could be a Nobel Prize. Maybe this weird outlier is the secret to understanding dark matter. But maybe it's just a mistake. A few years ago, there was an experiment where they had neutrinos generated in Switzerland, and they were going through the earth, and they were detecting them in Italy. And they calculated the time, and they realized they were able to make the neutrinos go faster than the speed of light. And everybody was really excited and really confused for about 6, 7, 8 months until they figured out they had their equipment configured a little bit wrong, just a tiny bit wrong. So that outlier was a mistake. So to answer your question, there's no easy answer to outliers. Who asked about the outliers? Yeah, there's no easy answer. Okay, so cleaning data. Once you have clean data, then you start to explore it, just look at it. A lot of people do big data science projects and not even actually look at the data. Print it on the screen, put it in a file, look at it, get it put up in your head as something that you can think about and dream about and process. Oftentimes when I'm doing something difficult, I have to look at it, sleep on it. Next day, try again, sleep on it, try again. And it's the process of having it in my head while I sleep and do whatever goes on when I'm dreaming. I connect the dots. And then some morning I'll wake up, and while I'm hearing the alarm and I'm not quite fully awake yet, I remember it and then I know what to do. That's happened to me a lot. Modeling the data. Okay, once you understand the patterns in the data, then maybe you can figure out a way to model the data. That means make some machine learning thing that can either predict part of your data or generate data like your data. That's generative AI. For instance, we know we can model images really well because we can generate them. How many of you have played with Stable Diffusion or Midjourney or Lensa or heard of these, where you can use AI to make an image? It looks real, doesn't it? And this started a while back before it was popular, before everybody was talking about it. You go to this person does not exist. Who's heard of this? All right. Every time you refresh this page, you get a new person that doesn't exist. AI randomly made this. This is not a photograph. And of course, it makes weird mistakes all the time. Like, why is there human hair floating out here in the air, right? I'm just going to refresh it. Here's another person that never existed before. Here's another one. This is generated from scratch, from a random number. And what they did is they trained a neural network to recognize faces. And then they just played the same neural network backwards. That's the basic gist. These people have never been seen before because they do not exist. It's amazingly good quality work, isn't it? These look so real. Someday, these people will be actors in your TV shows and movies. It'll be a sad day because we won't have actual movie stars anymore. And you can see how sometimes the long distance interactions aren't quite right. Like these eyes aren't looking quite in the same direction. Although there are people for whom that's true, it's probably just an error. Sometimes I see weird things in the teeth. Sometimes I'll see people who have the frames of the glasses, but not the part that goes to the ear, or vice versa. Anyway, it's remarkable technology, and people have done it for other domains as well. On this foot, there used to be this shoe does not exist. Okay, I don't know if that is. Okay, this shoe does not exist.
Oh my. You might be getting an email from.
This shoe does not exist. These are not real products. That's obviously Nike, right? But Nike had nothing to do with this. Nike hasn't sold this product. And that's New Balance, okay. Adidas. Adidas again. Not sure. Adidas, this one looks dirty, like it's been run, someone's been running with it. Not sure what brand that's supposed to be. And it looks like you've got white space and a little piece of it just floating out in the air. So what they did, same thing with the images of the people. They took millions of these, or whatever, however many they had. They created a neural network that could recognize them and then played that backwards. And that's definitely not something Nike would put out, because the swoosh is messed up a little bit. And that swoosh is too short. And who knows what that is? And that's just all kinds of mistakes. Although maybe it's supposed to be mistakes. I think I saw one of you today has a shoe somewhat similar to this. Saw it in the hallway. Anyway, people are getting creative these days. That's what it means to model the data. Maybe you can predict something about it, or maybe you have a model that can generate things like your data. Now, I hear some of you moving. I think we have another 5 minutes. So don't leave yet. Okay. This is an example from the book. You'll gather data, you'll clean it, you'll explore it, maybe you'll model it, and you'll interpret. Now, this model, has anyone ever seen something like this? It's kind of, but it's kind of not, because it looks like the data points are on the bottom and on the top. And this right here is a smooth line in between, but it's not exactly matching the data points. This is typically how you show a logistic regression. And what it's saying is that if you're down here, the probability of the 0 state is higher. But once you go above 0.5, the probability of the 1 state is higher. But there are other data situations where you want to do curve fit, fitting lines of data. But this is a different one. And some of you will deal with things that are binary, zeros and ones, or yes and no in this case. This happens to be a fraud example. And we'll do this next time. All right. Any last questions? Does everybody know when my office hours are? All right. I will see you guys on Tuesday.